Okay. All right. So we're starting with this new chapter. We started already yesterday, but let me just remind you a couple of things. Um, we start with what we call a maximum and minimum, right? So maximum is the highest point in the domain. Okay. So this is shown in here. Okay. And the minimum is the lowest in S. S is the domain. Whatever, not necessarily domain, but whatever you think of is located inside. Okay. Minimum maximum is called the extreme. Okay. So this is the okay, and the F that we try to find max or min is called objective functions. Okay. If you just I don't need to we don't need to rewrite this thing. Okay, so when does the function have a minimum or maximum? Okay, to ensure it has a max min, we need f to be continuous, functions continuous, and on the closed interval. Okay, so this is the case when you don't have a max nor min. See, it extends to the right, so it goes to infinity. And let's see, this is 1 over x. Right. Let's see. On 0 infinity, without the 0, that means without the left end, you see that it has no min nor max. Max because, well, approaching 0, it keeps going on, keeps increasing. So there's no max. And to the left, sorry, to the right, it keeps decreasing. So there is no min in this case. However, if you say restrict this on say 1,3 here, right? Then you have max here and min here, right? So this continuous and closed interval. Okay, and when the extreme occurs, okay, so this is max, max, min, max. But here the max is in the left end, min is in the right end. Here the max is somewhat in the middle, but min also here. And max also can be attained in this kind of fashion here in a corner. So the hard bend of the graph. Okay, so all right, so let's start from here. It's called stationary. Okay. All right, so let's I should have start screen instead. Okay, let's move to the all right. Has the display changed to OneNote?
Yes, sir.
So let's see what we call a critical point. So this is the classification of what we call a critical point. Use this blue. Okay. F critical equals A if one option is E equals 0. All right. or does not exist, or is a we call it border point, endpoint. Okay, so in this case, this is called a stationary. This is called singular. This is endpoint. Okay, so pictorially, stationary. Well, this tells you that the slope of the tangent is zero. So that means this the tangent exists, tangent line exists, and it is horizontal. So this tells you that the tangent line exists, it's horizontal. Okay, and singular. Well, we know that the derivative doesn't exist if it is a, say, not continuous, or a H, how do you call it? Corner. I would say just corner. Okay. So in stationary, this is the case. There we go. Or something that looks like this, or there. Because the if you think about the tangent here, there, or there, or something like this. This horizontal tangent. And if you think about singular, singular looks like this one. Yes, or or corners. So this is the what you call singular. Okay. All right. So what our concern about the critical point? Okay. And sorry, this is critical point. Critical point. Critical point. What we call critical point is a f of a. This is critical point. Point correspond to a coordinate. So it has x coordinate and y coordinate, and it obtains at x equals a, right? So x equals a is not the uh, critical point, but the critical point must be up here, right? And the thing is that we have this critical point theorem. Okay, it says that if f of c is an extreme value, that means c is this is extreme point. Then c must be critical. Okay, so what's mean critical? So it's either an endpoint of the interval, so left end or right end, or a stationary point, which is the has a tangent, horizontal tangent, or a singular point. So it is a corner thing. Okay, so this that's the reason we need this critical point, because we would like to determine extreme point. Okay, so in B, right? So let's go back this. Say, what do we write this? Good point. Okay. I won't rewrite this one. Okay, I'll refer to this one. So to find x beam of, of function f on interval I, what we need to do is find all critical points. Okay, and okay, so let's see the okay, first. Okay, so let's example, give you some example how to find the critical points. Let's say x 2/3, and from x that's defined for all x. So let's say this is from -5 to 5. Okay. Find all critical points. See, and all their type and their type. Okay, first let's compute the derivative. The derivative is 2/3 x to be -1/3. So this is something that you can write as x this. So it's not defined at 0. So undefined at 0. So it's, we can say is that um, here exists at any x in, sorry, the endpoint doesn't count. Okay. Except for x equal 0. Okay, so that's why this is the um, say which is singular, and x equal -5 and 5. Those are the endpoints. So those are the only critical points. Okay, no stationary. Okay, and from this, uh, how we find the whether it is max min or nor neither of them. Max or min. Or neither. Okay, so we need something more here. Right. Let's go back to the textbook. Okay. Extreme. And we will need this one. We call monotonicity. Okay. So F is increasing, increasing just an intuitive idea. For example, here to the right of C, this is increasing. To the left, and this is decreasing. You're in determining whether you have decreasing or increasing, you have to move from the left to the right. Okay. Because from C, if you're moving to the left, you're going up. So it's increasing. But no, because you have to go from the left to right, then to the left of C, it is decreasing. Okay, so that's the idea. Okay. So what's the idea of the monotonicity? Decreasing and increasing, decreasing, we call it monotone. Okay. All right. This is a monotonicity theorem. It says that if the derivative is zero, then f is increasing. Okay, and if this derivative is negative, okay, and f is decreasing around that point. Okay, so by determining the sign, we know how f behaves around that point, whether it's increasing or decreasing. Okay, we'll postpone the proof for this one. Evident. Okay, so it works both way. This is theorem A. Let's go back to the OneNote. We call this F is a bit paste them theorem A here actually. All right, so um, F is and F is increasing. On the other hand, it's negative as it's decreasing. Okay. On the other hand, we have also if f is a differentiable, interval, And if f is increasing on this a interval, then the derivative is positive, and decreasing derivative is all right. So if you combine them, you have it works both way. That means you can indicate decreasing or increasing just from the sign, and yeah, and vice versa. Okay, so monotonicity depends on sign of derivative. Okay, so let's do some example. So let's find some example. In this case, let's find one. All right, let's do this example one from the book actually, but let's do this in detail and what it tells you about. Okay, so we would like not only to find increasing or decreasing, but we would like to find its max min. Okay, so we find the critical points. Okay, one. Um, given as 2q 3x squared minus 12x plus 7. Or let's see, sorry, I forgot to do this. 5 to 5 percent. Okay, find all critical points. Okay, so how to do this one? All right, so let's do this first. Okay, critical points. So critical points. So we'll find the derivative. Okay, we find the derivative. Let's compute this easy. X squared minus 6x minus 12. So we can factor this out, take the 6 out, and let's see what's left. 2x, no, just one, minus 2. And this factors to x minus 2, x plus 1. Okay, so critical points are x equals, here this negative 1 and 2. This is a stationary. Why stationary? Because if you plug in this gives you derivative equals 0. Okay, and what else? Because it is always differentiable, no uh, no singular. So f is polynomial, f prime. Derivative always exists. F prime exists everywhere. But we have on the other hand, we have this one here. That's our, what do you call? Uh, endpoints. Okay, so those are the critical points. All right, so what we need further? Further, we need a sign chart, monotonicity. We need sign chart. All right, so how do we draw a sign chart? All right, so let's indicate the all the critical points here. Okay, so -5 and 5. So that's the endpoint, right? And then x -1 and 2. If 1 and 2, the scale is not really important in this case. Okay, so let's just find charts. Just indicate this is for f prime. Okay, so you can check the design by plugging in numbers here to the f prime. So if, for example, here you plug in 3. You plug in 3, this gives you 3 minus 2 positive, 3 plus 1 positive. So you have plus here. Okay. And of course, we can now use this if this is factorized or factored. So across 2, here's the factor. Power 1, so it changed the sign. So across -1, it is this power 1 also. So it changed the sign. Okay. So what we can say is that because positive or negative of the derivative has to do with monotonicity, what we can say is that, well, it goes going up here, going down here, going up again. Okay. So what we can say is that is increasing on from -5 to -1 and from 2 to, that's what we know, and decreasing on, see, -1, 2. Okay. And what do we know further? This should be, all right. What we know is that uh, the function must be continuous. So you have to be able to connect this increasing and then decreasing. So what you have is that when you connect, you get something like this. Connect something because this is stationary. Okay. So now you know this is the where's the max would be located. You would guess. Okay. So the max would be, all right, where to find the max? How to find the max? Just from the picture here, how to find the max?
The max is the one where it goes up and then goes down. The gradient, the derivative.
Let's just notice from here. Here, or let's see, what, this cannot be the max.
Set at next x negative 1.
Don't know yet, because we have also this one here, right? So it's still going up here. It is possible that this is stop here, like going up and stop here, but it is also possible that it's going up until 5. So this is the max in this case. All right, so you still have two possibilities, -1 or 5. Okay, just make comparison now. Okay, so by comparing f, oh, let's find this out. Plug in -1, what you get? Plug into the functions, not to the derivative. What is f -1? Here. -1, this is 2, -1.
14?
14, right? F5. Oh, this is going to be a big number. 5, this is 125, so 250 minus, this is 25. 100 what?
122.
Okay. 1422. So in this case, you would find max would be next x equals 5 endpoints. Maximum value would be 122. Maximum point is there. Okay, so you see there are 3 attained at here. This is maximum value. This is point. All right. And similarly, if you need to find the minimum, you just need to make comparison between f of 2 and f of -5. Next, split to find min. Okay. If you plug in 2, what you get if you plug in 2? 2 and -5. Let's go back to this function. f of 2. 2, this is 8, 16, 4 minus 12, minus 24 plus 7, 4 minus 20 minus 13. And f of negative 5 is, I guess this is going to be even lower, because this is going to have you negative, there, okay. This is not a negative. Oh, sorry, this is, yeah, this is negative. Because negative 24, 70. All right, so this is lower than this one. So negative 5 is the minimum. Min is obtained at x equals negative 5. All right. So first we would call this stuff here. We'll call this one is a, say this is local. This looks like a max, but the max turned out to be here, right? So we call this, well, this is local max. This one here turned out to be the absolute max or global max. So we would like to distinguish whether you have a local thing or the whole thing. Okay, so what is local max? Local max, this is the highest in this area. Okay, there is some intervals here around that point, around -1, so that at 1 that is max. So you don't have to compare with uh, other critical points. And this one also we call local min, because this is the lowest uh, on this interval. All right. So you can say, well, this is a champion of a, from a kampung for a desa or something, and this is the champion for the whole world. Okay, so this one we call local max, local min, and global max. So let's write this down. So what we call global max or min. So this is the highest, right? Or the lowest, and the global min, and local min max or min is the highest or the lowest plus point on a small neighborhood. We call this neighborhood. Say this is interval around that point. Okay. So for example, if you have something that looks like this one, okay. So this is the n. So you can say, oh, this is the all the local max. Okay. And actually this one is also the global max or absolute max. Right? While the uh, here, those are the local min. And it seems that also this one is also the absolute min. Okay. All right. So that's how to find the max or min. Okay. So without picture, what we need to find max or min. Let's go back to this one. Let's see. First, find all critical points, and then compare on those critical points. The largest would be the max, smallest, the lowest would be min. Okay? So you have to find absolute extreme, including the endpoints. Okay, we'll do some more example. All right. Um, see by sign chart. Okay. So, for example, you have a sign chart like this one with this change of sign. This is plus minus. We have four types. Let's use this. Minus plus, plus minus, plus plus minus minus. Okay, by using theorem A, what we know is that suppose this is the critical point. Okay, and we have a sign like this one. So what we can say is that here you have this going down, it's going up. This is going up and coming down. This is up and up. This is down and down. Okay. So here what you have is that because it's a continuous, so you have to be able to connect to the left and to the right of A. Okay. And in this case, then you have a local min. Here you have local max. Okay. So min is attained if you're going down and up, down and then up. Max is going up and down. Okay. This is they both neither max nor min. Okay. Neither max min. Okay, so let's do some more example after this. Okay, so let's take a break for 5 minutes and then we'll start again.